All right, thank you everyone for coming today. So as advertised, I'm going to give you a reinforcement learning tutorial, and then that'll last for roughly an hour, and then we'll do some exercises. Hopefully everyone saw there's a GitHub repo with some code in it, and there's a specific set of exercises for you guys to try. And what we'll do is, after I'm done talking, you can either work on your own or split into groups. I'll give you a very quick demo of how to use the code, and then we'll try to regroup after you do one or two of the exercises. Now, in terms of this tutorial, first I should preface by saying that I don't really care how much of this I get through, so please, by all means, interrupt me at any time and ask questions, and I'm happy to expound on any point, because needless to say, reinforcement learning is a huge area, and I'm not going to really be able to do justice to the whole discipline. The other thing about this tutorial is it's a little bit non-standard in the sense that instead of jumping right into a kind of standard introduction to reinforcement learning, like value functions and the Bellman equation and prediction errors and all that kind of stuff, what I'm going to actually do is try to introduce you to reinforcement learning through the lens of classical animal learning theory. So I'm going to start actually with the Rescorla-Wagner model and then try to show you how that very simple model can be elaborated in a number of ways, one of which leads to reinforcement learning algorithms. And I'll try to connect this along the way to things like maximum likelihood estimation, Bayesian inference, and a few other ideas. Okay. So just to ground everything, and throughout I'm going to try to ground this as much as possible in actual empirical data, actual experiments. So let's just imagine a simple Pavlovian fear conditioning experiment. So you put an animal in this box, and you play a tone. That's typically called the conditioned stimulus. This tone doesn't have any pre-existing associations for the animal, so the animal doesn't do anything when you expose it to the tone. But you then pair that tone with a shock. So this is an unconditioned stimulus. It has some innate motivational value for the animal. And if you do that repeatedly, and for fear conditioning, you only need to do it once, really. And when the animal hears the tone, it's going to freeze. And that's its fear response. It's an anticipation of upcoming shock. So that is the basic Pavlovian fear conditioning scenario. And what associative learning theory basically says is that what's happening during this conditioning protocol, what the animal is acquiring, what information the animal is acquiring about the world, is an association between the tone and the shock. And so all of associative learning theory is really about what is the nature of that association, the algorithms that give rise to it, and so on. Now, I should say that there are many problems with that, and in fact, I've spent a lot of time trying to kind of argue against that simple view of associative learning. But I think it's useful, at least for exposition purposes. OK, so what are the basic claims of associative learning theory? The foremost claim here, if we think about this as a very simple kind of reinforcement learning, that what the animal is acquiring is an association between states, actions, and rewards. Now, I'm going to be a little bit wishy-washy with what exactly a state is. There's a mathematically precise notion of state in reinforcement learning theory. But for now, let's just assume that a state is the stimulus. It's something that's useful for predicting immediate reward. And then the crucial claim about learning is that the modification of these associations is driven by prediction errors. These are the discrepancies between what the animal expected to get and what it actually got. And I'll elaborate on the nature of those prediction errors. Now, probably the most influential idea about associative learning, the most influential formal idea, was introduced by Rescorla and Wagner in 1972, and it's come to be known as the Rescorla-Wagner theory. I'm writing it in a way that they wouldn't have written it, in a more compact vector notation, and hopefully people aren't too afraid of vectors and matrices. But let me just unpack what this means. So we're going to imagine that you have a collection of cues, conditioned stimuli. So those cues, the presence or absence, or in some cases the intensity of those cues, can be encoded by a vector, which I'm representing by x. And the n index here denotes the trial number, right? So this is going to be a trial level model. I'm going to describe things as though things are happening exactly at the same time, trial by trial. And I'll come back to some of the limitations of that soon. So we're going to imagine this vector of Q activations or presence or absence indicators. And for each of those Qs, there's an associated weight. And the weight encapsulates the association between that cue and the expected reward. So that weight vector is represented here by W. And the basic idea is that after observing a reward, Rn, the animal is computing a prediction error, delta n. So that's the discrepancy between what it actually observed and its expectation, which is denoted here by Vn. And so this prediction error says that when the animal got more reward than it was expected, so it was a pleasant surprise, that positive prediction error should lead to strengthening of the associative weights. And if you got a negative prediction error, so you got less than you expected, then you should weaken those associative strengths. And that's embodied by this equation here. So what we're imagining here is that the value, your expectation is encoded by a linear combination of the cues. So in essence, if we think about these as being present or absent, this inner product just says that I'm going to sum up all the weights of the currently active cues, and that leads to my immediate reward expectation. And then what I'm going to do is I'm going to update the weights in proportion to the prediction errors, but only for the cues that were present. Okay, so that's an important part of this theory, which is that you're only updating the associations for the present cues. And that turns out to be actually a weakness of this theory, as I'll show later. Okay, are there any questions about this so far? Yes, go ahead. Rn is, well, in some sense you can say that Rn is coming from the environment, right? It's the shock, let's say, in a Pavlovian fear conditioning experiment. But actually, more generally, Rn should index something like the animal's hedonic state, right? So that could be subject to certain kinds of internal variables, not necessarily the objective reward from the environment. Any other questions? Okay, so I want to show you. All right, well, before we get into a few examples of this, let me just give you a sense of why this was such an important idea, just from a scientific perspective. So, first of all, the Rescorla-Wagner model was able to explain a huge number of empirical phenomena in classical conditioning. And in fact, some of these phenomena were predicted by the model and subsequently tested. And I'll tell you about a few of them. Scientists studying fear conditioning leaned heavily on this formal framework. I mean, not so much explicitly, but kind of implicitly, it represented the general theoretical framework in which they were operating. And they basically mapped out the detailed structure of how these computations could be implemented by amygdala circuitry as well as interactions with medial prefrontal cortex. In appetitive domains, this has often been these kinds of prediction errors have often been associated with dopamine signaling, and I'm going to come back to that later when I talk about temporal difference learning. Okay, so what I want to do now is kind of go through with you guys together and try to work out what the predictions of this model are for certain very simple animal learning paradigms. So just to familiarize you with this kind of notation, I'm labeling the different cues by A, B, and so on. The arrow means that it's predicting, it's leading up to some outcome. So plus indicates a reward or a shock, it doesn't matter. And a minus indicates no shock or no reward. Although in this case, we're not using any minus signs here. So for the purposes of mapping this onto some simple math, let's imagine that plus denotes a reward value of 1. So if we think about this equation, let's imagine that every time there's a plus, we have a reward value of 1. And let's also assume that all of the weights get initialized to 0. Okay? And again, the x's here, the x vector denotes the stimuli that are present or absent on in the current trial. So it's 1 when the stimulus is present and 0 when the stimulus is not present. So let's think about this this paradigm, which is known as forward blocking or Cayman blocking. There's unfortunately a tendency in the animal learning literature to name phenomena in this very tendentious way, which actually proffers a theoretical explanation for the phenomenon. So it's an unfortunate logical usage. So let's think about the very first phase where we have A associated with reward. So what happens to the weight for A if you do that repeatedly? it increases in what will it asymptote to? Can you? No, because if the weight goes above 1, then you're going to start getting negative prediction errors. Or sorry, positive prediction. There's negative prediction errors, yes. Yeah, so it's going to asymptote to 1. So at the end of this initial conditioning phase, the weight for A is going to be 1, and the weight for B is going to be 0 because the model didn't observe anything above B, right? OK. So now we present A and B in compound. So what that means in the context of the Rescorla-Wagner model is that these two weights are going to be summed together, right? So what is that going to equal to? 1. Yep. OK. So we have a prediction of 1, and we have a reward of 1, right? So what's the prediction error going to be? 0. OK. So what does that imply about learning in this phase where you get this compound A-B presentation? No learning, right? Because the Rescorla-Wagner model depends critically on prediction errors to drive learning. So as a consequence, A's association won't change, but neither will B. So A's weight is going to stay at 1, and B's weight is going to stay at 0. And so what does that imply for the final test when I present B by itself? No response, right? So it's nice to stop for a second and dwell upon what this means. It actually is somewhat counterintuitive, right? Because it says that simply pairing a stimulus with reward is insufficient to cause that stimulus to acquire an association with the reward, right? B has been paired with reward repeatedly and yet has acquired no associative strength. That's surprising in a way. So this phenomenon is called blocking, based on the intuition that the association of A is blocking B or somehow explaining away the reward, and hence B can't claim any credit for it. Any questions about that? OK. We don't have to go through this one because it's a very similar logic. This is known as overshadowing, where I simply take out that first phase. So I'm now just presenting A and B together, and I test B. And here, B will acquire some associative strength, but less associative strength than if it was presented by itself. Because one of the key tenets of the Rescorla-Wagner model is that these two stimuli are going to be competing for associative strength. Now, the last phenomenon I want to talk about is really interesting. This is actually a phenomenon that was anticipated by the Rescorla-Wagner model and subsequently confirmed experiment. So everyone knows what happens here. A and B both get weights of, let's say, 1, assuming it was trained to asymptote. Sorry, I realize this may be a little bit low for people in the back to see. OK, so now A and B get paired together with a reward of 1. What should the reward prediction be when you present A and B in compound? What should the V here be? 2, yes, 2, right? Because at the end of this conditioning phase, both of these guys have weights of 1, so you come up that should be a value of 2, right? So what does that mean for the prediction error? If I'm getting a reward of 1 and I predicted 2, now I have a negative prediction error. Okay, so I have a prediction error of -1. So now if I subsequently test B, what is going to be my response to B here relative to at the end of conditioning? Weaker. That's right. So again, this is actually quite counterintuitive if you stop to think about it, because in all of these phases of the experiment, all of the stimuli were presented with reward, and yet I'm actually weakening the associative strength of B as a consequence of reinforcing it, right? Rather surprising. Question? Yeah. OK, so just so everyone heard that, the question is, I don't understand how B gets weakened. So remember, all the modifications of these weights is driven by this prediction error, right? So when the prediction error is positive, the weights get increased, and when the prediction error is negative, the weights get decreased. And so what we're saying here is that on these trials, you expected reward of 2 units, because A and B both predict 1, and they summate, so they'll predict 2. And yet you got a reward of 1. So that leads the prediction error to be negative. You're getting less than you expected. Yes?
Why present together? You present it using together, you get the reward as 1. Why the Rn is 1?
Well, the Rn is just stipulated by the experimental paradigm. So I'm stipulating that when I present these together, I pair them with a reward. In other words, if I wanted to get a 0 prediction error, I'd have to present them with twice as much reward because they're expecting twice as much. Right? Does that make sense? Yes?
So why would you even integrate these together if they're not
well, this is, I mean, I don't want to, we're not trying to do anything here. We're not trying to teach the animal anything here. What we're really doing here is demonstrating some surprising predictions of animal learning theory, and in particular the Rescorla-Wagner theory. So, because naively you might think that pairing stimuli with rewards should be a sufficient condition for reward expectation. And in fact, increasing it, and you should certainly not think that pairing stimuli with rewards should decrease your reward expectation. And yet here it is. This is known as over-expectation. The animal over-expects reward, and it gets a decrease in its prediction. Does that answer your question? Yeah. Okay, any other questions? So hopefully everyone's got a flavor for how these models work. You know, it's really simple to just think through the equations here and generate predictions. You don't even have to simulate this model. You can just think about it. It's great when you have models like that. Okay, so this is just what I explained to you just now. And there's many other phenomena like this. So I want to offer now a probabilistic interpretation of this model, right? So this was just a bunch of equations that made some predictions about learning, but I haven't said anything about the normative basis for these equations. And in fact, most of the time people don't say anything about the normative basis. But you can actually write down a probabilistic model such that implementing Rescorla-Wagner will compute something that is normatively justified. So I'm going to write down the generative model in a way that's somewhat more general than is necessary for explaining the Rescorla-Wagner model, but it will come into play soon when I talk about generalizations. So here's the basic generative model. And in case people aren't familiar with this kind of probability notation, let me just quickly go over it. So this n here denotes a normal distribution. So when I say that there's some variable that's drawn from this normal distribution, so I'm taking a random sample of a normal distribution with some mean and some covariance matrix, okay? So I'm assuming that the initial weights were drawn from some normal distribution with a mean of 0 and some covariance matrix, which is just a scaled identity matrix. So the identity matrix is just a matrix of all zeros except for ones along the diagonal. So this just says that there's some number, sigma squared w, which is along the diagonal of this covariance matrix. Don't worry too much about the details of this. Now, the second thing that happens in the generative model is that the weights change slowly over time. So this is just a very simple kind of Gaussian random where the weight at the next trial is drawn from a distribution center at the previous trial and just basically diffused slightly over time. And then finally, I assume that the rewards are drawn, just as in the Rescorla-Wagner model, through this linear combination of this inner product between the weights and the stimulus features. In other words, I'm taking a weighted combination of the stimulus features to produce reward. Now, this is actually the point where people often get confused, because I'm using the word model, but the model here has a really different, very sense than the model that I was presenting to you before. So the model I was presenting to you before was a process model or a mechanistic model. It's a model of the psychological computations that we think the animal is executing. This is a generative model. These equations are not happening in the animal's head. This is a description of the internal model of the animal has of the world. So it's the animal implicitly makes these assumptions about the world, and then the actual computations it does is to try to make a set of observations. So it observes the cues and rewards, and then it tries to recover the trajectory of the weights over time, right? So the computation that the animal is trying to do is estimate these weights somehow, and this generative model supplies a set of inductive constraints on the animal. Does that make sense to everyone? If that's not clear, please ask questions now. Yes?
Shouldn't it be prediction rather than reward?
Prediction rather than reward? No. So I'm kind of doing a little bit of abusive notation here. I'm just reusing this notation of a linear combination of weights and cues to denote the mean reward. And then the reward is actually drawn from a Gaussian centered at that mean. Does that answer your question?
I'm still a bit confused.
Yeah.
Reward is something that, as you said,
Yeah.
it's kind of experimental. So
Yes.
and the prediction is something about the animal. So how can
Yeah, so that's what I meant by a Bayesian notation. So forget that this is called Vn. This is just saying that reward is a linear combination of the stimulus features. So this is nothing in this model is explicitly nothing in this model is really explicitly represented by the animal in the sense of the mechanistic computations. This is the structure of the animal's assumptions about the world. What it's claiming is that the animal thinks that rewards are generated by linear combination of the stimulus features, and it's trying to figure out what that linear combination is. Okay. So this is known as a linear Gaussian generative model for those of you who care. Okay. Okay, so here comes the crucial part, which is that I'm not going to go through the derivation, but basically you can show that if you take this model, then what the Rescorla-Wagner model actually is what's known as a stochastic gradient method. So it's this generative model, and it's taking the gradient or the derivatives of the likelihood with respect to the parameters. So the parameters are represented by these associative weights, and it's following that gradient to estimate the weights. So it's basically doing a kind of stochastic maximum likelihood estimation. So it's taking the stochastic part refers not to the stochasticity of the algorithm, but rather to the fact that the animal is getting random samples of experience, and it's taking these little samples, maybe one trial at a time, and updating its estimates of W. And what that does is if you do that for long enough, and you have some constraints on the learning rate, then W will converge to the maximum likelihood estimate. In other words, it will converge to the value, the animal's estimate of W will converge to the value that maximizes the likelihood of the animal's experience data.
Do you have a problem with local versus global maximums?
Not in this kind of generative model, yeah. Okay, so this is our kind of first taste of what it means to connect a normative model of associative learning to actual mechanistic model. So there's nothing about the Rescorla-Wagner model that commits us to an interpretation of maximum likelihood estimation, but it at least gives us a way to connect these kinds of normative principles to what the mechanistic model is doing. Yeah?
How important is it that these are novel distributions as opposed to other kind of distributions?
It is somewhat important. You don't necessarily have to make all of these assumptions to get this result. But this is kind of the most standard set of assumptions. Okay, so what's missing so far, right? So far, it seems like Rescorla-Wagner is a pretty good model, right? However, there's actually two limitations, one of which I'm going to talk about now and one of which I'm going to talk about a little bit later. So the first limitation is that we can think about the Rescorla-Wagner model as a point estimation algorithm. What that means is that the animal estimating a single value of the W's that it's going to use to generate predictions, can be prediction errors, and so on, right? So it's a single point in the space of all possible weight vectors that it could estimate, right? However, probability theory suggests that the proper representation of the animal's uncertainty should reflect the fact that actually there are many possible weight vectors that could give rise to the data. In fact, an infinite number of weight vectors that could give rise to the data. And so the animal should really be representing a whole subjective probability distribution over those weights. And that's the basis of Bayesian this kind of generative model, and I'm going to talk about that next. I'll just briefly flag that the other limitation of this, as I mentioned before, is that it's just predicting immediate reward. In fact, we've just broken down the task artificially into these trials, but real life doesn't consist of trials, right? Real life happens in continuous time, or at least in some much more fine-grained chronology than discrete trials. So we need to think about how to extend this model to deal with that, to deal with the fact that things can happen within a trial, that you can have delayed reward, and more generally, how do we deal with kind of the continuous flow of time? All right, so if we're going to take seriously the idea that the animal might be representing a probability distribution over weights instead of just a single point estimate, how should we think about that? So first of all, what is the normative principle? The normative principle, as you probably can guess, is Bayes' rule. So Bayes' rule says that if I want to compute the posterior distribution over weights conditional on the history of my observations, and I'm kind of simplifying things here because this should also be conditioned on reward history. So all the stimuli plus rewards up to trial n, that posterior distribution is proportional to the product of two terms, the likelihood of the data conditional on the weights and the prior of those weights. So the likelihood tells you if I posit a particular weight vector, how likely were those observations? How well predicted were my observations given a hypothetical weight vector? And then the prior is saying what set of weight vectors are more likely before I've even observed any data, right? Because not all weight vectors are equally plausible a priori. So this looks a little bit scary, but don't worry about the details here. I'm going to just explain the key principles here. So this is actually, it turns out, a really standard model in signal processing known as the Kalman filter. That if you make those Gaussian assumptions that I showed you before, the posterior distribution is also a Gaussian with some mean and covariance matrix that can be updated analytically according to the Kalman filtering equations. The Kalman filtering equations are the Bayes optimal solution to a linear Gaussian dynamical system. What's important to notice is that the weight update here looks almost exactly the same as we saw before. You have this prediction error that's driving change in the weights. But here, instead of having a single learning rate, you have this whole vector of learning rates, or in signal processing terminology, those are called the Kalman gains. And the Kalman gains depend on this covariance matrix, which represents the animal's uncertainty about the weights. It's important here to dwell on exactly all of these terms. I just want to highlight some aspects of these things. So the first thing to point out is that if you don't observe anything, your uncertainty is going to grow monotonically with time. That's what this term is showing you here. So basically, whenever I observe something, I'm going to subtract some portion of covariance away from this covariance matrix. But if I don't observe anything, this goes to 0, and then I have this additive term into the covariance matrix. So this is the intuitive here is that the weights are changing slowly over time. And if I don't make any observations of the cues and rewards, then my uncertainty should grow. As it happens, my uncertainty will grow, but the posterior mean will stay the same. And another thing that happens as your uncertainty grows, learning rate will increase. And the intuition here is that in all Bayesian inference, there's always this tension between the likelihood and the prior, right? In other words, how much do you trust your data and how much do you trust your prior beliefs? And when your uncertainty grows with time, you're going to tend to differentially trust your data because you have basically weaker and weaker prior beliefs over time as you fail to observe any data. Okay, so that's a key prediction of this model, that uncertainty is going to grow with time, and hence your learning rate is going to grow with the passage of time over when you haven't observed any data. Any questions so far? So I want to illustrate what this model does for two phenomena. So the first is called backward blocking. Backward blocking is a lot like forward blocking, which I showed you before, but we've just reversed the order of phases. So we're going to first present A and B in compound. So this is kind of like in an overshadowing procedure. So you presented A, B in compound, so you've acquired some associative strength for both of them. That will be somewhere between 0 and 1, because remember, they're competing for associative strength. All right. Then you present A by itself, predicting reward. And you present B alone. Now recall from the Rescorla-Wagner model, you can only learn from present stimuli, right? So since A is being reinforced here, but B doesn't appear in this second phase, B's associative strength should not change according to the Rescorla-Wagner model. But in fact, it does change empirically. So empirically, we find that B's associative strength goes down. So this is really problematic for the Rescorla-Wagner model and prompted a bunch of researchers to try to make ad hoc modifications to the learning rule that would allow it to learn from absent stimuli, but in the opposite direction, basically making the learning rate negative. But as it turns out, the Kalman filter version of the Rescorla-Wagner model resolves this nicely because that kind of just falls out automatically from the model. Yes? Like in actual experiments, yes. So well, it depends on what kind of animal you're studying and what particular preparation, but whatever you're using as your index of the conditioned response, that is going to go down. Like, well, in Pavlovian fear conditioning, that would be the freezing response. So how long, what proportion of time are they freezing? Yeah. Okay, so how does the Kalman filter? The basic idea is that when you do this first conditioning phase, in the Rescorla-Wagner model, it's going to estimate both of these associative strengths to be 0.5. But in fact, are only one of an infinite number of weight vectors that would predict an outcome of 1, right? Because all that has to be satisfied is that the weights sum up to 1, right? So we can think about a whole distribution of weight vectors that satisfy the constraint that they sum up to 1. But because you have a prior that says that the weights should be close to 0, then some of those weight vectors are preferred over others. And in particular, the weight vector that's most preferred is where both of them have 0.5, right? So you have this kind of contour that favors some weight vectors and not others. All of them are consistent with the data. The other important thing is that because of the constraint that they sum to 1, if one of the weights increases, the other one has to go down in order to continue satisfying that constraint. And that is implicitly encoded by the covariance matrix that's learned during the course of this compound conditioning. So the off diagonals of the covariance matrix reflect the interdependencies between the weights of the cues. So how one weight will change when the other cue's weight changes. And that's what gives rise to this kind of the model's ability to learn about stimuli that were absent. Because of that negative covariance, when you present A by itself paired with reward, that you learn not only that A's associative strength would increase, but also that B's associative strength should decrease in order to remain consistent with the constraint that they sum up to 1. And that's the logic of how B's associative response decrements. Any questions about that? Okay. So this is a big jump in a sense from the assumptions of the Rescorla-Wagner model and lots of models like it, because all of these models assume that you're only learning about present stimuli. This is not learning about absent stimuli. And it turns out I'm not going to go into this, but I'll just flag it. And if you're interested, you can read this paper that I wrote a few years ago in PLOS Computational Biology, which describes how actually there's a huge number of phenomena in animal learning that are incompatible with the Rescorla-Wagner model in this specific sense in which you can learn about absent stimuli. And the Kalman filter model can nicely explain a wide range of those phenomena. Maybe in the interest of time, I'm going to skip this. Actually, I should mention it just quickly because it's in the MATLAB code. So there's another phenomenon that causes problems for, which is that, again, remember, you can only learn when you're getting positive prediction errors. But latent inhibition, in the latent inhibition paradigm, you present a cue by itself without any reward repeatedly before then conditioning it. And the phenomenon is that that acquisition of that conditioned response is slower if you've pre-exposed the cue prior to conditioning. That's problematic because there's no the cue weight starts at 0 and you get 0, so there's no prediction error. There should be no learning. The Kalman filter model can deal with that because the uncertainty associated with that cue weight is going down over time. So even though the mean is staying the same, because you repeatedly expect 0 and got 0, you get a stronger and stronger confidence that it really is 0. And hence, when now I'm pairing it with reward, I'm telling you that actually, no, it's not 0 after all. It should be a reward of an expectation of 1. Your prior is going to be pulling you back towards 0. And that's why acquisition is retarded after Q pre-exposure. Okay. Yes?
Yeah. So just to sort of run from, so the
Yeah.
Bellman filter model is the Rescorla-Wagner model? It's just like an implementation of it?
No.
Or,
Yeah.
or is it like considered a separate model in the literature?
Well,
Yes.
it's not considered very much at all because people who study animal learning don't study signal processing. But but actually, it was proposed a while ago by Peter Dayan, and sort of only a few of those really cared about it. But I think it's a really powerful idea, so hopefully people will care about it later. It's not an implementation of a Rescorla-Wagner model. So I'm taking a kind of Marian approach here. So I'm saying that there's there is an internal model that the animal has, like that's the computational level analysis. The animal is making some assumptions about the world, and now the animal has to has to define some algorithm for doing inference in that model. So the Rescorla-Wagner model, and sorry for the overuse of the term model, the Rescorla-Wagner is an algorithm for estimating the weight vector, and it corresponds to a kind of maximum likelihood estimation, which constructs a single point estimate of the weights. The Bayesian version of Rescorla-Wagner entertains a whole distribution over the weights. And if you make these Gaussian assumptions, then you arrive at a common filter, and that's what the common filter model is. It's the Bayesian version of the Rescorla-Wagner model. Yeah?
There are many other filtering algorithms, so you have some support for
Well, the support are some of the examples that I just showed you, and there's some other. I won't, that's a good point. So there are other filtering algorithms. Some people have even suggested that algorithms like particle filtering could even explain how animals update even better, because one of the curious phenomena that you see in animal learning is that it seems almost to be stochastic. And the common filter is completely deterministic algorithm. So whereas particle filtering generates stochastic samples as estimates of the posterior distribution. And so some people have suggested that that kind of algorithm could give rise to the observed stochasticity of behavior in animals. Okay, so basically that's the end of the classical learning theory. And now what I want to do is link that classical learning theory, which is operating at the trial level, to sequential decision problems. And that's really the provenance of reinforcement learning proper, reinforcement learning as conceived by computer scientists. So this would be kind of the beginning of a standard lecture on reinforcement learning. But hopefully I'm going to connect all the dots. All right, so here's an example of a sequential decision problem. This rat is trying to maximize its food intake. And so to do that, it has to plan some kind of sequential decision policy through this maze. So I'm denoting different states here, S1, S2, S3. So notice that now here are states I'm talking not about particular cues, but locations in a maze, and more generically, anything that is going to be able to predict future states and rewards. So broadly speaking, there are two computational strategies for solving this problem. So one, which is known as model-free reinforcement learning, tries to build up a table of values. What a value is the cumulative future reward that the animal expects to get when taking a particular action in a particular state. So we can build this lookup table that tells you how much cumulative reward the animal expects to get when, for example, it's in state 1 and it goes left. Okay? I'll tell you in a moment about how you could actually learn these values directly from experience. And the key idea of model-free reinforcement learning is that it doesn't have any, it's not building up an explicit internal model of the world that I'll describe to you momentarily, but rather it's just trying to directly estimate this lookup table from trial and error. And once you have the lookup table, if you're in a particular state, all you have to do is inspect the lookup table to choose the action with the highest value. And this kind of algorithm is what's most classically associated with the firing of dopamine neurons. And I'll go into that in a little bit more detail momentarily. An alternative strategy is known as model-based learning. And the basic idea here is that the N was going to construct an internal model or a cognitive map of the world. And what that means here in a sequential decision, you'll learn a transition function. So where, if it's in a particular state and it takes an action, what state is it going to go to next, or possibly what is the distribution over next states? That's the transition function. And then the reward function is how much reward it expects to get in each particular state. Okay? So once you have those two pieces, then you can put them together through a variety of algorithms to construct plans. So for example, you can use dynamic programming algorithms or maybe more intuitively some form of tree search. So that the idea is that if you have a transition and reward function, you can basically simulate different paths through this environment and pick the action that is going to lead you along the most profitable path. So these two algorithms have different computational trade-offs. The model-free system is very fast because remember, to compute action values, you just have to inspect the lookup table. However, it's very inflexible in the sense that remember, the value function is defined as a cumulative future reward. That means that there's a coupling between your immediate reward and all your future rewards. As a consequence, if the reward function changes, then you have to change all your values in that lookup table, and that could require a lot of relearning. So it's inflexible in that sense, that if there's some change in the environment, you basically have to relearn everything. Whereas the model-based system has the opposite set of operating characteristics. So it's highly flexible in the sense that it's representing its knowledge about the world in a kind of modular way. So if the reward at some state changes, all you have to do is change the reward function at that particular state, and through whatever computational mechanism you're using to compute value, that reward will immediately propagate to all of your values. Now the downside is that that's computationally expensive, so it's going to lead to slow, effortful computation. Because doing some kind of tree search is always going to be more effortful than inspecting a lookup table. So just to get a little bit more formal with this, so I said the value is the cumulative future reward. In many cases, what we really are going to compute is the discounted expected future reward. So the reason that we're going to introduce this exponential discounting term is so that the values don't diverge to infinity if we're thinking over an infinitely long planning horizon. And more psychologically, we can say that this discounting is basically just stating that you value your near-term rewards more than your long-term rewards. And then this expectation is average of this quantity over the randomness induced by stochastic state transitions and rewards, and possibly stochastic actions as well. Okay. Yes?
Is it important that the future discounting decays exponentially, or?
It is, yes. Yes, it is important. This is not the only choice of objective function. But to get what I'm about to talk about next, you need exponential discounting. So if you have exponential discounting and you've made what's known as a set of Markov assumptions about the world, in other words, if you make the assumption that when I'm in a particular state depends only on my current state and my action, in other words, my transition is conditionally independent of my history given my current state. And likewise, my reward depends only on my current state and action, not on any of the past states and actions that I may have visited earlier. Those two Markov assumptions suffice to write down the value function in a recursive form, right? Because if you just look at it this way, it's pretty impractical, right? How are we going to estimate this thing that's an infinite sum? But it turns out that if you make the Markov assumption and you have this exponential discounting, then you can write the value function in this recursive form known as the Bellman equation. So it just says that my value at my current time point, and notice that I'm indexing by t now because we've escaped from trial level land. So we're just talking about however we've defined time, which could occur within a trial. So my value at time t is equal to my immediate reward plus a discounted expected future the next time step. Okay? Yes?
Such consideration mechanism
Observation of what?
It is correct, but the point that was can be considered
Mhm.
elements of something, not to exclusive hypothesis.
Well, I agree that they can be considered elements of a continuum, and I wasn't going to get into that just in the interest of time, but I'm not sure the continuum here is about these statistical estimation issues of overfitting, because you can overfit for model learning, also overfit for estimation of this lookup table. So they both have this property, right?
Well, there's some definition about which you can define. And the question is, where do we put professional? Along that question, where do we put professional for the evidence of one place?
Yeah.
Where do we put evidence of one?
I think this is a really important issue, and I think it's probably realistically going to be too complicated to get into here, because it turns out that model-based and model-free learning actually, the computations can get enmeshed with each other in many different ways to the point that the distinction kind of blurs. And that's actually sort of one of the main things that I research. But I think for our purposes, let's just run with this distinction now and keep in the back of our heads that it's not as strict as I'm making it out to be. Yes?
So you said we have the market assumption.
Yes.
So for most papers of CML people,
Yeah.
this RL, like QN and any other.
Okay.
Is it one of the main reasons that they really fail their kindergarten is that they have this assumption like this?
Well, no, because model-based and model-free algorithms, at least the ones that I'm describing, all depend on the Markov assumption in some sense. Of course, you can develop algorithms that don't depend on the assumption or relax it in certain ways. But the key difference is not about the Markov assumption, but rather how you respond to changes in the environment. And if you're forced to respond to changes in the environment by changing your lookup table, or in the case of like a function approximation algorithm like a DQN, you're changing the parameters of this function, your knowledge is going to be necessarily inflexible in the sense that you can't kind of selectively change one piece of your knowledge about the world. You have to kind of change all of these different weights in your network, or all of these different cells in your lookup table. That's kind of the main limitation. OK, so the reason why the Bellman equation is very important is because it's the basis of many efficient algorithms for value function estimation. So let me explain to you one particular one. So what I want to ask you to do is think about just taking this equation, right? This is just an identity, if we've assumed that these are the true values, and subtract v of t from both sides. So now I have this equation that I've written up here. And if my values are correctly estimated, then this quantity on the left side should be 0. Right? Because what the Bellman equation basically says is that there's a consistency between the consecutive value functions at consecutive states. Right? So if that consistency condition is violated, it tells you you've misestimated your value function. Not only does it tell you you've misestimated, but it tells you in what direction you've misestimated it. Right? So if you've overestimated your values, then you're going to get what is effectively a negative prediction error. It says that you should reduce your value estimates. And if if it's a negative prediction error, if it's a positive prediction error, then you should increase your value estimates. So what we have here is a prediction error that's conceptually similar to the prediction error that we saw already in the Rescorla-Wagner model and the Kalman filter model. But the key difference here is the introduction of this middle term here. Right? So if we imagine that this is 0, now we just have immediate reward minus your value expectation. So you can see actually that if the discount factor goes to 0, we're just back at the standard Rescorla-Wagner model if we use this prediction error as the learning scheme. But by introducing this middle term, we can induce these values to take on long-term expected future reward, not just an estimate of your immediate future reward. So I introduced all that machinery for Rescorla-Wagner and Kalman filter so that you could see that this is really a kind of temporal generalization of the same basic ideas. Yeah, so I didn't tell you what the learning equation is. So here's the learning equation. So the important thing to note is that, oh, sorry, should have put it up here. So this is the same exact learning equations that you saw before. The only difference is the change in this prediction error term to introduce this middle term here representing the discounted future value at the next time step, right? So it's, again, it's the same equation as the Rescorla-Wagner model, essentially. And in fact, when Sutton and Bardo were developing this theoretical machinery, they were inspired by animal learning phenomena. And they saw this actually, they did some of the pioneering work in applying temporal difference learning to animal learning phenomena. So this is known as the temporal difference learning model, and this prediction error here is known as the temporal difference prediction error. Okay, any questions so far? Since we've now gone from trial level models to continuous time models, we have a little bit of an extra complication, which is that we have to think about how we represent the world, right? So in an animal learning experiment, I'm showing you these cues and some outcomes, but now cues are extended in time. So how are we going to represent that temporally in the context of this kind of model? And people have proposed different kinds of representation. I'm not going to go too much into it. The standard one is called the complete serial compound, which is basically to imagine that the stimulus is on for some period of time, break that duration down into little bins, and for each bin, I'm going to define a feature. So that feature, so this is like the x vector that we were talking about before, a particular feature is only on at a particular offset relative to the onset of the stimulus. So at the beginning, this feature's on, then this feature's on. It's just the stimulus onset initiates this cascade of features that terminate when the stimulus terminates. That's called the complete serial compound. It turns out that from an empirical perspective, this has some limitations, which I'm not going to go into today, and led other people to propose variations like what's the microstimulus model, where we have these temporal functions. So one way to think about this is you can imagine in your brain a bunch of neurons that represent time cells of various, or sort of stimulus-locked time cells. So they're active after some onset, and maybe they have some boxcar tuning curve, or maybe this is a smoother tuning curve. And that collection of neurons represents a basis set for estimating the value function. Yeah? Sorry, choice condition? Oh, trace condition. Yeah, I wasn't going to get into that. I mean, I haven't talked about things like eligibility traces, which will preserve short-term memory of past stimuli, and that may be necessary for capturing things like trace conditioning. For various reasons, this turns out to not necessarily be a great way to represent time for the purposes of learning. Like, there's a lot of arguments about whether this is even a sufficient way to properly treat temporal conditioning phenomena. So let me give you one example of why this kind of TD model is useful from the perspective of modeling animal learning. So in a second-order conditioning scenario, I initially condition a first-order with an outcome. So let's call the first-order stimulus CSB. This is from a paper by Sutton and Bardo, which was applying the model that they developed to animal learning theory. So I initially pair CSB with some reward, and then I pair CSA and CSB sequentially, but without any reward, right? So this is the time course. So CSA comes on, then CSB comes on. So CSA is referred to as the second order stimulus. And notice that CSA is never getting paired with reward, right? So classical learning theory should not predict that it acquires any associative strength. But the Rescorla-Wagner, the TD model crucially does. The reason is that if you think about this, so your immediate reward is 0, but your future value is going to be positive because CSB predicts future reward. So even though no immediate reward is presented, the value function for stimulus B can propagate reward expectation to A. So as a consequence, repeatedly repairing CSA and CSB together will cause CSA to acquire some associative strength. Eventually, that's actually going to go down back to 0, which is something that is seen experimentally. So one of the main reasons we care about TD learning is actually not about from the behavior, because actually that Sutton and Bardo paper was published in the early 1990s. But no one really cared about the TD model until a paper by Wolfram Schultz, Peter Dayan, and Reed Montague came along, this famous science paper in 1997, where they showed that the TD model seemed to be able to describe some detailed characteristics of phasic dopamine responses in the midbrain, that is, phasic responses of dopamine neurons in the midbrain during classical conditioning. And these were responses that had initially puzzled investigators like Schultz before they were elucidated by Dayan and Montague. So if you just present a reward by itself without any cues, just free reward, you will see bursts of dopamine neurons, bursts from dopamine neurons. However, if that reward is predicted, for example, if that reward is predicted by some cue, so the cue reliably predicts reward, you actually won't see a dopamine burst in response to the reward. Instead, you'll see a dopamine burst in response to the cue that predicted that reward, right? So you should see that this immediately contradicts what's the kind of popular view of dopamine as a kind of reward molecule. Because if it was just reporting reward, then you'd expect it to respond when reward is delivered, regardless of whether that reward was predicted or not. But in fact, it only responds to unpredicted reward when reward is surprising. And that's the key contribution from the TD model, which is to explain why that happens. Because once the reward is fully predicted, there's going to be no longer any prediction error. And according to the TD model of dopamine, the dopamine response is reporting these prediction errors from the model. And that, in fact, the model predicts that the prediction error should backpropagate to the earliest reward predicting stimulus. And likewise, if you expected a reward and that reward was omitted, then you should get a negative prediction error. Now, firing rates can't be negative, and in fact, dopamine neurons already have a very low basal firing rate. So what you see is this little pause here in the dopamine firing. Any questions? OK. I want to make sure that you guys have enough time to do all your programming. So I'm going to make this last part really quick. I wanted to try to connect all these dots. So far, we've seen the Rescorla-Wagner model as a kind of point estimation algorithm for immediate reward, and the Kalman filter as a Bayesian estimation algorithm for immediate reward. Now we have the TD model as a point estimation algorithm for value, right? So cumulative future reward. So to close the loop, what we need is a Bayesian version of TD learning, just like we had a Bayesian version of Rescorla-Wagner model. And it turns out that actually you can get this almost for free using the same mathematics that drive the Bayesian version of Rescorla-Wagner. And the way to do this is, again, to assume that that the value is a linear function of the stimuli. And then basically, through a little bit of mathematical rearrangement, you can get it so that the immediate reward is a linear function of this thing in parentheses, which is basically like a discounted temporal derivative of the stimulus vector. In other words, I'm looking at how the stimulus, instead of associating the stimulus vector with reward, I'm associating the time derivative of the stimulus vector with reward, how the stimulus is over time. Don't worry if that's not too intuitive. The main reason that I wrote it this way is because now we're basically back to a Kalman filter. Because remember, the Kalman filter, all the Kalman filter needs is to have these features that enter linearly into a prediction for reward. We have that. So basically, what we can do is run the same exact Kalman filter model, but instead of inputting x into the model, we input this thing, this time derivative, into the model. And all the equations are exactly the same. And again, it preserves this property that the prediction error signal is still, the TD error signal is still the driving force for learning in this kind of model. But now what we're estimating is not just a point estimate of the weights, but a mean and covariance matrix for the weights. OK, and so just to give you a kind of graphical explanation of what I just showed you, we can think about all models along two dimensions. what kind of estimator they are. So are they Bayesian estimators or point estimators? Right? So Bayesian estimators, remember, estimate a whole distribution instead of just a single point or a single value. And then what is the target? In other words, what are they trying to estimate? Are they trying to estimate immediate reward or value? Okay? So this organizes all the models that I just told you about into one coherent framework. And probably in the interest of time, I'm not going to tell you about some of the experimental applications of Kalman TD, the Bayesian version of TD learning, but suffice it to say that there are a number of, it turns out that there are actually a number of phenomena that aren't really well explained by any of these models that I already told you about, but can be explained by this Bayesian version of TD learning.
Model like DQN is only using QN.
Wait, say that one more time?
DQN is basically using QN.
Yes, the DQN is using TD learning. Yeah, there is a world beyond DQN. Yeah. So maybe what I should do is stop there, and I can take more questions, and then maybe we can jump into the programming. Have I exhausted you? Yes. Yeah.
The animals estimate the body function. What kind of algorithm do you think the animal use to improve the policy?
That's a great question. So yes, I shamefully didn't tell you about policy improvement, and I just basically pretended that we're only doing value estimation. But of course, a big part of reinforcement learning, maybe the main part of reinforcement learning, is finding a good policy. So there's a number of different solutions to this. So kind of the classical solutions like Q-learning or SARSA are based on the idea that you can kind of straightforwardly extend the value estimation algorithms that I already just showed you, TD learning, but into account that the values depend not just on states but on actions. And if you want to learn more about, I mean, the best place to learn about all of this stuff is Sutton and Bardo. And in fact, there's a new edition of Sutton and Bardo that you can download from Rich Sutton's website, and it now has like 100 pages on neuroscience. There are other algorithms like actor-critic algorithms, which are based on a different idea, which is a form of policy gradient. So the basic idea here is that there's a critic which is trying to estimate value functions, just like I showed you. So basically, if you want to use this in an actor-critic, you could have TD learning or even Kalman TD learning as your critic. It's just estimating state values. And then you have a policy, that's your actor. The policy is a mapping from states to actions. And that policy is being criticized by the critic. So the critic, the policy generates some actions, and then the critic computes its prediction errors, and the prediction errors are used to guide the actor's action. So it turns out that if the prediction errors are positive, then that tells the actor, okay, you're doing a good job. Increase the probability of taking those actions that you're taking. And if it was negative, you're doing a bad job, decrease those probabilities.
Is the animal directly estimate policy by QI?
Yes, that's right. You can adapt everything that I told you in fairly straightforward ways to value learning for state action values, and then all that's needed is to have a mapping from your values to your policy. So the standard way to do that is to use a soft equation, for example. But I haven't gotten into that here. Yes. Right. So reward is your immediate reward. It's just how much reward am I getting now? Value is my long-term reward. What is the cumulative reward I'm going to get into the future? Right. So it's like reward is that was a really good donut, and value is I'm going to feel sick later. Yeah. Yeah. Sort of a little bit of both. I mean, Rescorla and Wagner are sort of really experimentalists at the core. And in fact, I don't think that they ever wrote another theory after that, or wrote another computational model after that. It was all experiments. There were some phenomena had already been known, like Kalman blocking, forward blocking, and I think also overshadowing. But things like over-expectation, backward blocking, all of that stuff was covered later. And in fact, at that time, they already knew about a number of things that were not consistent with Rescorla-Wagner model, even when they formulated, and they sort of already knew that. Like all the work by Tolman, which I have a bunch of slides on here that I didn't show you, which is about the evidence that animals have a kind of cognitive map that is learned independently of reward in some sense. Like that animals can acquire geometric representation of the environment independently of reward. That's totally outside the scope of the theories that I talked about. That's more in the realm of model-based learning. Does that answer your question? But just to finish the thought, many of one of the beauties of the Rescorla-Wagner model is that many of the phenomena were inspired by the Rescorla-Wagner model. It's a great example of a theory that sort of launched 1,000 experimental ships. Yeah. TD learning is the kind of classic example of model-free reinforced learning. It's not the only form of model-free reinforced learning. All right, so shall we do a little bit of programming just to give you a feel for this? I tried to, hopefully you all had a chance to look at this repo. So let me just, so this is the repo, for those of you who haven't seen it yet. I tried to write down these equations, write down these models in a very compact way, and with a lot of annotations, you could see what they look like. And you'll see that the models are super simple. Like apart from a little bit of stuff up here to do the initialization, we're just talking about a few lines of code. And even models as complicated as Kalman TD are also just a few lines of code, right? That's the whole model. So I encourage you to, if you guys are interested in using any of these things, to actually just look at the code and try to get a feel for how it works. But I also created a set of simulations, simulate models, which will give you an example of how to actually use this code to generate simulations, for example, of second-order conditioning. And I made some helper functions like construct stimulus, where you basically just tell it how long the trial is, the onset of the stimulus, the duration, and it will create one of these representations of the stimulus for you. So how to actually run a simulation, you have to construct the stimuli and the rewards, and then that's all you need, basically. So in the second-order conditioning example, I set up the stimuli and rewards, and I can run the TD model and the Kalman TD model. And there's a bunch of that's just annoying because it has to reshape the matrices to get them in a nicer format for visualization, and then it plots them. So you should be able to just very easily run these simulations. You just give it the name you just call simulate models and the name of the simulation. And then, are there any questions about that? And maybe that's the first thing you guys should all try to do. If you click on the wiki button up here, I have, here's the reference to the paper that I mentioned, which describes all of these models. And then I created simple exercises, which, if you guys want to do them, will just give you a sense of how to actually implement these. And once you've tried to do that, you can check them against the actual answers, which I put in this function exercises. So what I'd suggest for you now is, first of all, if you have questions, ask me. And then maybe work by yourselves or in groups and try to actually implement the first exercise. And after like 15 minutes, we can regroup and talk about how it's gone. Sound good? Yes.
Where is the?
It should have been on the right, but you can also just if you just look up here, it's github.com/j Gershm.
I think it's just under your GitHub.
Yes, if you can find my GitHub